Okay, everybody, thanks for coming back. We are again talking about acceleration. So this is kind of the second video that we're making for help, note help on acceleration. Okay, I've got a little picture here for you on acceleration. You can see we have point A, and point A is where this car is when we first start tracking its motion. And if you look at the picture, you can see that it is going to the right. Here at 34 meters per second to the right, that's its initial velocity. And you can see that we also have an acceleration then of 10 meters per second squared. And the arrows then are signifying the direction of the vector. So velocity is a vector, acceleration is a vector, and the arrows then are telling you the direction. So keep in mind, we talked the other day, we said that if we're talking vectors, and we'll just kind of go down here for a second, just talk vectors. If we're talking vectors, then we know that we have size or magnitude and direction. And I said that we're going to be dealing a lot with the math of vectors. And one thing that you have to kind of get different is the sign convention. So the question is, if you're doing a math problem and you have a negative sign in front of your vector, the question is, what does that mean? Well, we came up with the idea that negative is a way to signify direction. And the only way that we could say what direction negative is if we knew what direction positive is, or vice versa. So we have a positive and we have a negative sign that, when you do your math computations, you have to do everything just the way you're taught in math. But when you're doing vector math, then you have to realize that these signs mean something. And what they mean is, negative is completely opposite in direction by 180 degrees than our positive, okay? So if you have a number, for instance, if I say I have 34 meters per second, that alone is not considered really a vector because there's no direction. Now, we're going to be doing vector work a lot, so if we say this is a velocity and you know that it's a vector, then what's assumed here is a positive, okay? So if I said then I have a positive acceleration of 10 meters per second every second, and that would mean after 1 second of doing this, I would be going how far? Or how fast? Well, I'd be going 44 meters per second if my v sub naught equals 34 meters per second positive, and my acceleration equals 10 meters per second every second positive, then I would add this if my time was only 1 second. Now, if I did that for 2 seconds, then it would be 54. If I did it for 3 seconds, it'd be 64, and so on. So I think you're kind of understanding that part of acceleration and velocity. Now, the other question, though, is what happens if I have an acceleration that is in the opposite direction? So in other words, I start out with 24 meters per second. I'm going to call positive. And I'm going to say positive is in this direction. And I'm going to also say that my acceleration then is a negative 10 meters per second every second. So that means I'm going to change this velocity by this number every second in the negative direction, which is going to be in this direction. So if I do that for 1 second, my new velocity in meters per second is going to be 14 meters per second. If I do that for 2 seconds, my new velocity is going to be 4 meters per second. If I do that for 3 seconds, my new velocity is going to be -6 meters per second. See how that works? So what ends up happening essentially is that I start going in a different direction. So somewhere between here and here, I start going in a different direction. Implied is positive direction here, where I said it was that way, and somewhere between here, my acceleration caused me to go in the negative direction, which is that way. Okay, so that's kind of a side note here for you. I'm going to get back to our original car picture here. Okay, so we're kind of back on track. So you might be thinking, well, I have two positive numbers, but do we really have two positive numbers? Well, they are two positive numbers, but the direction in this case isn't given by the plus or the minus, but rather it's given by the arrows, so keep that in mind. So I'm going to ask you to answer a couple questions. The first question is, when will the car stop? Okay, so when will the car stop? Well, the reason why I picked this 10 meters per second squared is because, like I said, it's easy to do the math in your head with that. So let's think about this. 34 meters per second. Okay, well, 34, if I change my velocity in the opposite direction by 10 meters per second every second, after 1 second, the car is going to be at 24 meters per second, right? So at 1 second, it's going to be 24 meters per second. After 2 seconds, it's going to be 14 meters per second. After 3 seconds, it's going to be 4 meters per second. Okay, well, that's still not a stop. We're getting closer and closer and closer, right? To change this last 4 meters per second, is that going to take a full second? No, it's going to take 0.4 seconds. So at 3.4 seconds is when my velocity is equal to 0. So your answer for the first one is the car will stop in 3.4 seconds. Does that make sense? Yes, it does. Okay, so let's ask another question here, you guys. First was, when will the car stop? Number 2 is going to be, how long will the car stop? Okay, so this is kind of a tricky question. Okay, so if you look at this, acceleration is the rate and change of velocity, correct? So we know at some point, well, in 3.4 seconds, my velocity is going to be 0 meters per second. Okay? So what's going to happen at that time? How long will the car stop is number 2. How long? So I want a time increment for how long the car will stop. Well, you might be thinking, I don't know. Does it stop indefinitely? Well, if we are continuing to have a change in velocity of 10 meters per second every second, then the very next instant after the stop, there will still be another change in velocity. So 1 instant I'm at 0 meters per second. The very next instant I'm at some negative velocity. You know what it would be? Well, an instant is so small, you can't really define that. But it's going to be in the negative direction because this acceleration doesn't stop when the car stops. It continues to happen. Okay, so that's the answer to your second question. And to your third question here, your third question is, when will the car arrive back at point A? Okay, well, it took 3.4 seconds for it to come to a stop, correct? Has the rate changed on the way back? It hasn't changed on the way back, has it? So it took 3.4 seconds for it to stop. How long is it going to take for it to get right back from where it started? Well, if the rate of change is continuous to reach this velocity, and as you know, the average velocity will be the same going as it is coming, except for in opposite directions. It should take the same amount of time to have the same displacement. We kind of talked about that on the last video. So it would take 3.4 seconds to go back. So 6.8 seconds is when your car will stop. Okay, so now I got a little bit of an assignment for you that I want you to come in with tomorrow, or at least think about. And that's this. I'm going to have these graphs here. I have 4 graphs for you. And each of these graphs are going to be velocity time graphs. And I want you to explain what the motion is of the car in these graphs. Okay? These are all velocity time graphs, okay? Let me draw the actual graph in a different color. There's one for you. There's another for you. This is at 0. Here's another for you. And here's another for you. So there's 1, 2, 3, and 4. I need you to explain tomorrow in words what is actually happening in these graphs with the motion of, let's say, this car.